Hi, welcome to Engineering 255 Statics. In this video, we're going to start to look at the chapter 5, and the title for chapter 5 is Equilibrium of a Rigid Body. So it's different from previous chapters that we only concern about the equilibrium a single point. In chapter 4, we did start to look at the rigid body. When you have a rigid body and you apply force at a different position, you can make the body to rotate, and that's what we call the moment. So here we're looking at how do we find the equilibrium if we apply force and moment to a rigid body. We're going to focus on the first two sections in this video. The first section is conditions for rigid body equilibrium. To give you a definition of the equilibrium for a rigid body and the equation that you can use to solve the problem. The second section of this chapter is so-called free body diagrams. We did mention free body diagram before, but we're going to extend the idea about the free body diagram to a rigid body. You're going to learn more and more different conditions. How do you maintain a rigid body to stay in the equilibrium? So let's look at the objectives of this video. We wanted to let you know how to identify support reactions. This is the important topics when we look at the free body diagram. So the second topic is the free body diagram. We did going to give you the condition how to maintain equilibrium for a rigid body. So let's first look at some kind of applications for this kind of case. In this example that we show you right now, that you have a truck that has a ramp and it has a weight which is 400 pounds. And each of the ramp is pinned to the body of the truck. So what does the pin looks like? You look at the picture right here, and the pin is this position right here. This is a pin at the location of A. So what is the characteristic of a pin? The pin is something that allows things to rotate. So this ramp can go up, can go down, but it will be rotating about the point of A. So you are letting this ramp to freely move or freely rotate, not move, but rotate about point A. So that is the pin. But if you have a pin, would you get some reaction force? And the answer is yes. If you have a pin, you are allowed the things to rotate. So there is no reaction of the moment that will be against the rotation. So you are not going to have any of the reaction if you remove the pin. However, the pin is going to give you a supporting force in the X and Y direction, meaning the end of this ramp cannot just simply move like above or to the right or left of this point of A. So how do we idealize this model? How do we write an equation to model this? Now here you can see there are several forces. We have the weight that we always have to consider. Pounds actually is a unit of weight. You have the gravity, which is simply the weight, and that's 400 pounds. You also have cables. So cable always provide a tension. So this is the tension to the connecting point of the B. And then you have the pin, and we want this whole thing to be balanced. If you don't consider about these forces, it will never be balanced, because this force, this tension has the right and lower magnitude, and this one is going to the negative y magnitude. That means if we don't have a force in the x direction, actually toward to the negative x direction, this will never balance. And that's why you have this reaction force at here to balance it. Another example you can look at this is that you have two smooth pipes. Each one of the pipes is a diameter and is sitting on top of this L-shaped fork. How do we find out the reaction forces? To find out that, first thing you have to do is to identify what are the forces acting on this object. And that is important to select the object of isolate. Are you going to select the single pipe, or are you going to select both pipe? And the answer for this is that maybe it's easier if you select both pipes. So over here, the free body diagram shows the free body diagram of both pipes. You have the reaction force, which is the F at here and P at here. Both of these are coming from the bottom right here because you remove this L shape of the support. You also have a T force at here, which is another support coming out from here. Are there any supporting force at here? Well, if you consider both of the things as one single object, anything happen inside of this one is called internal forces. We do not consider internal forces if you're looking at the rigid body. And the reason is, if you think about the A is pushed by B, then B is also pushed by A, and the amount of push is going to be equal in opposite direction. So if you consider both together, the net force at this point is going to be 0. If you isolate just one single pipe, then there is a reaction force from either B to A or from A to B. All right, so that's first to think about what is the condition for the rigid body equilibrium. And the condition is very easy. It doesn't matter if it's a 2-dimensional, 3-dimension, the always condition is these two. So you have a net force equal to 0, you have a net moment equal to 0. The net force is a vector. So it could be X, Y, and Z direction. The moment you have to select a reference point. This reference point can be any point, an arbitrary point, any arbitrary point, and must be equal to 0. Okay, so that is the condition. If you think about the 2-dimensional, let's think about the 2-dimensional. How many equations can you get from here? You will have a summation of fx equal to 0. You will have a summation f of y equal to 0. You will have a summation of a moment with respect to a certain reference point equal to 0. So you have 3 equations. That means you can solve 3 unknowns. So let's go back to the previous problem that we just saw. Again, you have this ramp and you have a pin at the bottom here. Pin is the key that will determine how you can solve the problem or not, because you need to identify for a pin, what can a pin support? And we're going to see a different kind of a support. For the pin support, you're going to have an X direction of a force and Y direction of the force, but you're not going to have any of the moment as the reaction force. Let's look at free body diagram. So We are using an example to show you a different kind of support. In this picture right here, you see a beam from A extended to the right, and at the point of A, this beam is kind of embedded in a wall. And if this is a wall, this is what we call the fixed end, meaning this end is fixed. You cannot move up and down. You cannot rotate as well. If this is a fixed end, we are going to have a different reaction force when you do a free body diagram. When we do a free body diagram, we isolate the object and we cut off any of the connecting part, which is this part and here. When you cut that off, it can support an Y reaction, it can support X reaction, it can also support a moment, because you need to have this moment to counter when you remove this fixed end, when you remove any of the support. Now, the direction of these reactions is arbitrary. Sometimes when you look at the problem, you will probably know what the reaction looks like. For example, in this example, if you push a certain distance away from that with this much of the force pushed down, to prevent it from move, this one must have a reaction force going up, right? You must have a reaction force going up. Are there any reaction force going horizontally? Well, because there's no action force, no force applied horizontally, so this X will be equal to 0, because there's none of the force acting on the X direction. If you consider about the weight of the beam, then we can also put the weight of the beam to the problem like this and here. So if they give you the weight, which is 981 at here, you're going to put the weight at the center of the beam. So if this is a uniform, it's just going to be in the middle of the beam. If it's not, say you have a triangle beam like this, then your center of the weight is going to be like the centroid that we do in the chapter 4. So it's going to be one third away from the base. Okay, but for this case, it's a uniform beam, then you have the weight at here. And then once you have all this picture drawn correctly, and you just use the equation that we show you, that is summation of f of x equal to 0, summation f of y equal to 0, and find a reference point to find where the moment is going to give you the 0. And the easiest point in this case is going to be point of A. And let me tell you why. And the reason for that is when you select point A, these two forces, AX and AY, will not contribute to any of external moment, because these forces are just applied to the same point. So they are not going to have any of the moment. You only have the moment, which is a reaction moment of the moment A, exists at that point. So selecting a reference point is important. You certainly can select any of the point. You can select this point as well. You can select this point as well. So once you make the free body diagram correctly, and then we can start to label all the dimensions, such as the distance away from the reference point, because we need these to calculate the moment. And we mark any of the force that we need to solve. So in this problem, we have 3 unknowns, AX, AY, and MA. And we already show you the AX is going to be equal to 0 because there's no extra force acting on that direction. Okay, speaking about the support, let's look at the support in the two-dimensional cases. For the three-dimensional, there's some other special case that we will look at, but let's just look at the two-dimensional. This first case is called a roller. The roller meaning at the bottom of the support you have like a wheel at the bottom. If you have a roller, we're gonna assume the roller only have the supporting force, just like you put a ball on top of a ramp. It only give you one single point of the reaction force. So the force is always just going to perpendicular the contact surfaces between the roller and the contact surfaces. So that's the roller case. The second is called the pin or the hinge. The pin allows things to freely rotate but cannot move X and Y. So you have a reaction force. If it's a free rotate, there's no reaction. If it doesn't, that means you have a reaction. And this is what we call the fixed support. Most general cases that you have two forces, reaction forces, and a moment. Again, the direction is arbitrary. You can always select any kind of the direction and your answer will justify your assumption. There's a lot more different support reaction in your textbook. I strongly recommend that you spend some time to read those. In the exam, you are going to have this kind of problem. You have to know which kind of support will give you what kind of a reaction. The rotation is prevented by a couple moments. So again, this moment here is one of the things that you need to solve if you have a fixed end support. Let's use an example to explain this. So we're given an operator that apply a vertical force to the paddle, so the spring is stretched by 1.5 inch spring, right? Spring give you a spring force, which is equal to K and the change of the S, change of the length. The force in the short link at the B is 20 pounds. So to simplify this actual device, you can see this is a simplified picture of that. And so the force in the short link is this one right here and the B at here. This is going to give you a force which is 20 pounds. And the spring, because it is stretched, so it's going to create a strain force going this way as well. So this is an F of S, which is equal to K delta X, right? And your K is going to be equal to 20 pounds per inch. The delta S or delta X, which is the change of the length, is going to be 1.5. So you're going to put 1.5. Does it like extend? Does it compress? It actually is compressed, but once you know what direction the force is, it's okay that you can simply use whatever the change that you find here and just follow the direction of your F of S. Notice at A, we have a what? We have a pin. This is a pin. This pin doesn't allow this device to move up and down. It does allow this device, if especially this arm here, to move in the rotation, right? You can rotate about the point A. So that is the case that we have. So once you can draw the free body diagram like this, then you will be able to solve the problem. So our feet is apply a stabbing force at here. You have a reaction force for the pin, which is AX and AY. We have two other forces from the link and also from the spring force. Now the spring force is K, which is a 20 pound per inch, times the change of the length, which is 1.5 inch. And that's how you get the 30 pounds coming from. You also need to make the dimension of the length because it's important for you to calculate the moment. So by looking at this, you can immediately write down the equation of the motion to find the equilibrium situation. If you look at the summation of f of x, I only have 30, 20, and x at here. So 20 plus 30 minus ax equal to 0. Let's look at summation of y. Make the top to be positive. We have f, which we don't know how much that is. It's negative f. We have ay. Okay, that's only two forces in the y direction. Are there any other equation we can use? How many unknown do we have? We have 3. These 3 are unknown. We only have 2 equations now. We need third equation. The third equation is going to be summation of the moment of a reference point on your choice. I will use the point of A because it will help me to eliminate these two that I don't need to do any of the calculation for that. And this has to be equal to 0. And what is the moment around A generated by the forces on this device? We still have 3 forces. So this F at here is going to create a counterclockwise, so it's positive. What is the lever arm of this force to this A? It's not this distance. It's this distance. Okay, this is the distance you're looking at. So this distance is a 5 inch. And then we have this force, the spring force, is going to give you a clockwise, right? Clockwise is going to be negative. And what is the moment? Is going to be the force times the lever arm. In this case, the lever arm is 1 inch. So you have a 30 times 1. For this 20 here, it also going to be the same as this one here. You all have the negative one because it's a clockwise. And this 20 times, is it 1.5? No, it should be this total length here. That should be 2.5. And you make this one equal to 0. At this moment, you can solve the f directly using this equation. Once you find the f, you put the f back into here. You have 2 equations, 2 unknown, ax and ay. You can solve this problem. Let's look at the second example. So the second example is an unloaded platform suspended off the edge of the oil rig. And the platform has a mass of 200 kilograms. The key here is mass. It doesn't give you the weight. How do you find a weight if you are given a mass? Weight is going to be the mass times 9.81 in the SI unit system. So this is what the platform is, and let's see how we draw a free body diagram from this one here. You can see it's connected with a cable, and there's a cable go down as well, so cable kind of turn around on the top. And let's look at how we draw this. Okay, so we made this device isolated, And this itself has a weight, which will be just right at the center of this kind of a cage. And it has a weight right here, right? And it's going to be at the center of this object. It has a cable, so the cable will always give you a tension force like this. And are there any other force? Well, here you have a pin at here. If you have a pin, we're going to have AX and AY. So our free body diagram is going to be AX and AY at the pin right here. The center of the mass is going to give you the weight, which is not mass. And you have a tension force that go along the cable. So this is the tension force. This is the free body diagram. And once you have free body diagram, you're going to use the same idea, try to find out what is the summation f of x, summation f of y, what is the summation moment, and you're going to choose the reference point. If I'm going to choose, I'm going to choose this point as well. I'm going to put a here. That will be a lot easier to do the calculation. For this one here, this is not horizontal or vertical, so you have to decompose this one to be tx and ty, so you can do this calculation more easily. Okay, so that's how you solve the second problem here. All right, we spent some time to talk about this chapter 5.1 and 5.2, and first thing is that you need to know how to make a free body diagram of a rigid body. And also remember, support has a different kind of reaction. So we have three different kinds of support. We have a roller, we have a pin, we have a fixed end. There's not more that you can see from the book. The second thing we talk about is the condition. The condition of equilibrium, we have summation of F equal to 0. We have a summation moment of any reference point equal to 0. And that's the equation that you need to solve this problem. We're going to see you in the next video.